Hello everyone, this is MOHAMMAD ASAD AMIN, lecturer in Physics, Education and Literacy Department. Today I would like to deliver you a lecture on a topic diffraction of light from chapter number 9, first year physics. I hope you will find this lecture interesting and informative. Diffraction. The bending and spreading of light waves around any sharp edges or corner or through openings is called diffraction of light. As you see in the diagram that an obstacle has been placed in front of a light, and when light spreads, it bends around the sharp edges, and a lens is placed in front of these light waves, which after refraction forms an image on the screen. Condition for diffraction. Diffraction effect depends upon the size of obstacle. Diffraction of light takes place if the size of obstacle is comparable to the wavelength of light. Light waves are very small in wavelength. It ranges from 4 into 10 raised to the power minus 7 meter to 7 into 10 raised to the power minus 7 meter, which is the visible range. If the size of opening or obstacle is near to this limit, only then we can observe the phenomena of diffraction. Types of diffraction. Diffraction of light can be divided into classes: Fraunhofer diffraction and Fresnel diffraction. First of all, I will explain you Fraunhofer diffraction. In Fraunhofer diffraction, as you can see in the diagram, the source of light and the screen are far away from each other. Incident wavefront on the diffraction obstacle are plane. Diffracting obstacle give rise to wavefronts which are also plane. Plane diffracting wavefront are converged by means of a convex lens to produce a diffraction pattern on the screen. Fresnel diffraction. In Fresnel diffraction, as you can see in the diagram, source and screen are not far away from each other. Incident wavefronts are spherical here. Wavefronts leaving the obstacle are also spherical. Convex lens is not needed to converge the spherical wavefront. Diffraction grating. Diffraction grating is an optical device consists of glass or polished metal surface over which thousands of fine equidistant closely spaced parallel lines are being ruled. As you see in the diagram, in this diffraction grating we are having 100 lines per millimeter. Grating element. Distance between two consecutive slits lines of a grating is called grating element. If A is the separation between two slits and B is the width of a slit, then grating element is denoted by small d, which is equal to A plus B. Technically, you can find the grating element by dividing the number of lines with the length of the grating. Diffraction occurs in accordance to Huygens principle, which says that every point on a wavefront may be considered as a source of secondary spherical wavelets, which spread out in the forward direction at the speed of light. The new wavefront is the tangential surface to all of these secondary wavelets. Now, as you can see in the diagram that we are having a plane wavefront on which we have selected different points. Now, each point on this plane wave is a source of secondary wavelet. So, we can find the new position of the wavefront by drawing a secondary wavelets of radius equal to s is equals to ct, where c is the speed of light and t is the time. The wavefront at a later time is tangent to all the wavelets. Now we can use diffraction phenomena for the determination of wavelength of light by using diffraction grating. Consider two parallel rays of light R1 and R2 falling on a grating as shown in the diagram. After passing through slits, they are diffracted and brought to focus on a screen at point B, as you can see in the diagram, by using a convex lens. Draw a perpendicular PQ from point P on ray 1. Ray 1 covers a distance RQ which is more than the ray R2. Now here consider a multiple slit, and I am considering two rays of light R1 and R2 which are coming through two consecutive slits which are at a distance of D, and D here is called grating element, which is the distance between two consecutive slits and equals to the width of the slit or transparent region plus width of the opaque line. Now consider a right angle triangle RPQ. As you see, R1 is covering more distance than R2, so we can easily find this path difference RQ through this right angle triangle. Now in this right angle triangle RPQ, sin theta is equals to RQ upon RP, or RQ is equals to RP sin theta. Now RP in the diagram is equals to small d, which is equals to A plus B, where A is the width of the transparent region and B is the width of the opaque region. Now RQ is equals to d sin theta, which is our equation 1, where RQ is equals to part difference of R1 and R2. Now we know that for constructive interference at point B, part difference between R1 and R2 will be 0, lambda, 2 lambda, 3 lambda, or in general we can write m lambda, where m is equals to 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, so on and so forth. Therefore, RQ is equals to m lambda for bright point. We put the value in equation 1, we get m lambda is equals to d sin theta, where m is order. This equation is called grating equation and is used to determine the wavelength of light. M is called the order of grating and it is the number of bright or dark fringe obtained on the screen. For m equals to 0, theta is equals to 0, central bright maxima of 0th order. When m is equals to 1, theta is equals to theta 1, first order bright maxima, and part difference equals to lambda. when m is equals to 2, theta is equals to theta 2, second order bright maxima and path difference equals to 2 lambda. With an increase in m, fringes of decreasing width and less brightness are obtained. As you can see on the screen that the central bright maxima is of maximum intensity, and as you are moving for higher orders away from the central maxima, the intensity is falling. So diffraction pattern is not of uniform intensity, in fact it is a pattern of falling intensity. No order of line is possible when theta is greater than 90 degree.